And yeah, now we're going to start the session. So our first speaker today will be Yoshihiko Hasegawa, who will be talking about thermodynamic uncertainty relation in quantum systems.
Thank you. It is my pleasure to be here, and I would like to thank Mark and organizers to hold this super exciting conference. So today's my talk is about thermodynamic uncertainty relation, TUR. I think many participants know about TUR, but I would like to start by a little story about TUR. We know that higher precision demand more resources, but the TUR serves as a theoretical basis for this notion. So I'd like to start from some biological example of cost versus precision. So first example is concentration sensing. Because cells can estimate the concentration. Because for instance, bacteria has to move away from toxic substances. So they have to sense the concentration. And the primary question is how accurate cells can estimate the concentration. The Berg and Purcell show that by the limit. This is known as the Berg-Purcell limit, and because this is a receptor on cells, and this is ligand, and ligand bind to receptor and unbind from receptor, and this process can be described by stochastic process, like this one. So this is bound, and this is unbound state. And Berg and Purcell shows that by using the bound state information, the relative accuracy can be given by this equation. So here, this is a variance, and C is a concentration, and N is a number of binding or unbinding events. So this is proportional to dynamical activity in a sense of thermodynamics. And we show that by using Cramér-Round equality, the ultimate limit is given by this equality. And we can see that this equality is a specific case of TUR or KUR. So next example is a biochemical oscillator, and Clay shows that studies the accuracy quantified by this equation, this expression, as a function of number of cells, and they use per cell. And in figure A, there are 2 cells. And in figure D, there are 27 cells. And they experimentally measure this quantity as a function of number of cells. And experimentally found that this is proportional to number of cells, inverse of number of cells. Because energy is proportional to number of cells, this relation can be proved experimentally. So as can be seen, this is also a specific case of TUR. So let me start with some toy model. So this is considered in the original paper of TUR, and we suppose we have some ring model, and let K plus be the transition rate in the clockwise direction, and K minus be the opposite direction. And we are interested in the displacement within some time interval 0 to tau. And this is because this is a simple random walk. Average is given by this one, and variance is given by this one. And uncertainty, epsilon, can be quantified by variance divided by square mean. And for this simple case, entropy production rate can be evaluated by this simple equation. Then multiplying sigma tau epsilon, then they found that this quantity is bounded from below by 2. This is a very simple algebraic equation. Then which immediately indicates this thermodynamic uncertainty relationship. Although this bound assumes a very toy ring model and assumes displacement observable, TUR states that this relation holds for general Markov process with general current observable. So let me define the TUR in Markov chain, general Markov chain. So suppose we have a Markov chain described by this master equation here, And this is transition rate from M to N, state M to N, and PMT the probability of being M at time t. And by solving this master equation, we have some kind of trajectory, and we assign observable to each trajectory. And TUR are interested in observable like this one. Here, NMN is the number of transition from M state to N state, given some time window. And CMN is a matrix, which is a weight matrix, which can. So this is observable. Interested in TUR. So TUR can be classified into broadly classified into two groups. The first one is a current type one. This is the original TUR, and observable, defined in previous slides, is bounded from below by this quantity. Here, sigma is the entropy production within some time window, and phi is observable. And in this current type of TUR, this weight matrix has to be antisymmetric, meaning that this relation should be satisfied. And the other one is known as counting time and often referred to as KUR, kinetic uncertainty relationship. And a counting type is given by this one, and A is known as dynamical activity and quantifies average number of jumps within some given time window. And for the case of this one, there is no restriction on weight matrix C and M. So this type is more general than this current type. So there are many derivations for deriving classical TURs. This is some list of derivation, but this is not the complete list because I made this slide a few years ago, and I guess there are more, other derivations for deriving classical TURs. So today's my talk is not about classical. So my talk is about quantum generalization of TUR, and many presentations in this conference have indicated that it is important to consider the quantum clock, which can be implemented by, for instance, quantum heat engine. And quantum TUR can provide universal bound for quantum timekeeping devices. And quantum TURs have been studied in several papers, and I think that most of these papers consider some specific model. So in my talk, I introduce general quantum TURs and show connection among quantum TUR, quantum meteorology, and quantum speed limit and Heisenberg uncertainty relationship. So let me start from continuous measurement. And I think that for the review of continuous measurement, this archive paper is extremely useful. So basically, continuous measurement uses Lindblad equation, which is given by this one. H is Hamiltonian, and Lm is the jump operator of nth channel, and rho is density operator. And the Lindblad equation renders dynamics when we do not measure the environment. And on measuring the environment, the Lindblad equation is unraveled to yield the stochastic dynamics condition on a measurement record. So the quantum trajectories, this is an example of some quantum trajectory. So we have, this is a measurement record. So here's their jump. And depending on this jump event, the trajectory is given, like this one. And taking average with respect to measurement records, we have this dynamics, and this dynamics is governed by original Lindblad equation. So as I explained in classical case, we are interested in this kind of observable, which counts the number of jump from n to n. And similarly, in quantum case, we are interested in this kind of quantity. Nm is the number of jump of nth channel, and Cm is a weight vector. So this Cm can be arbitrary, real vector. And it is useful to represent continuous measurement as a matrix product state. This is original Lindblad equation, and if we consider very short time limit, time evolution for short time limit can be described by this Krauss representation, and here MZ and MM is a Krauss operator. And using this Krauss operator, we can represent, we can define matrix product state corresponding to this continuous measurement, which is given by this one. So in this representation, this psi s is a state of original Lindblad equation, and this state, this corresponds to environment or field records the jump record. So if we have this matrix product state, MPS for short, we can recover any information. So if we are interested in a jump event, then we measure this part. And if we are interested in the main part, then we can measure it here. And so the continuous measurement is like this one. So within some short time, we have some environment, and then it is interact with the main system. And after the interaction, we measure the environment. And this diagram is identical to this one. So when we want to obtain the information of jump records, we have to measure the MPS state at the final time. So this is identical to measuring the continuously. Then if we consider the continuous limit of MPS, we have CMPS, continuous MPS. So CMPS encodes classical and or quantum stochastic processes into quantum field. So for instance, suppose we have this kind of Markov process. So we have two states, and there's jump at S1, S2, S3, and S4. This information can be encoded in the field by this one. This is a vacuum state, and by using the field operator, satisfying the commutation relationship, we can create a particle in this vacuum state. And the CMPS can be represented by this expression. So this is a field state, this is a system state. And by applying this operator to this state, we can obtain CMPS. So CMPS includes all the information about the continuous measurement, including both main system and jump reports. So I would like to first review the classical primary round equality, which will be used for deriving TUR. So we are interested in the classical parameter estimation. So suppose we have some probability distribution which has unknown parameters theta. In order to estimate this theta, we have to sample distribution. So suppose we have some data given by this D. Then using this data, we estimate the parameter using some function. The primary round equality gives a limit of the accuracy of this estimation, which is given by this one. And here, f theta is a feature information. And there is a generalized primary round equality, which is given by this representation. Then, of course, there are quantum estimation, but it's a little bit different. For the case of classical estimation, the classical estimation can be performed by this figure, but for the case of quantum estimation, we have to define how we measure quantum state. So for quantum estimation, we have some quantum state which has parameter theta, but there is a degree of freedom on how we measure this quantum state. And after defining this measurement, POVM, then latter process is the same as classical estimation. So quantum estimation is more difficult than classical case. Then, yes, so quantum primary round equality gives lower bound for the variance of parameter estimation theta. And this FQ theta is known as the quantum feature information. And because, as I said, the degree of freedom for the quantum case is larger than the classical case, QFI, quantum feature information, is difficult to calculate in general. But when the system, quantum state is pure state, then it is known that QFI can be calculated with this representation. So by using the quantum primary Rao equality, it is possible to obtain quantum TUR, which holds for steady state case. So we have some hypothetical parameter theta and parameterize Lindblad jump operator and Hamiltonian as this one. And with this parameterization, the system speed is faster than the original dynamics by 1 plus theta. So by applying, this is a quantum primary Rao equality, and the observable is number of jump events, so it can be represented by this one. Then we can obtain this representation. And here H is a parameter which depends on type of continuous measurement. And because, as I said, quantum feature information is very difficult to calculate, but for pure state, it is not difficult. And as I emphasized in this slide, CMPS state is pure state. So by using this CMPS representation, quantum feature information can be calculated with this expression. And we calculate the quantum feature information. It is known that the quantum feature information can be calculated via two-sided Lindblad equation. For reader, please see this paper. And for steady state case, we arrive at this representation for jump measurement case. Here T is time duration, and this epsilon is a frequency of jump, corresponds to dynamical activity, and this psi is coherent term contribution, and this is difficult to calculate, even difficult to represent. So this is copied from my paper, but it is not easy to understand. And so this is a simulation of the result. Suppose we have some atom driven by a classical laser field, and E and G are excited in ground states. And for this simple system, the dynamical activity contribution and coherent contribution can be calculated analytically. And this is a numerical simulation. And when the bound is satisfied, all the points should be above this dashed line. And this green plot is a bound corresponds to this one, which does not include the coherent contribution. So we see that the quantum case is more accurate than classical case. And as I mentioned previously, quantum primary Rao inequality holds for arbitrary measurement. In this case, arbitrary measurement corresponds to arbitrary POPM. So this means that quantum primary Rao bounds holds for arbitrary unraveling. So let us consider diffusion measurement. Then the H term becomes 1/4. Then quantum TUR becomes this representation. So when using diffusion type measurement, accuracy is 4 times better than jump measurement. And this is an example of observable, and this is a simulation result. And this dashed line is 1/4 of jump measurement case, and this dot line is a jump measurement case. So we see that some points are below this dot line. So jump measurement yields more accurate than diffusion measurement is more accurate than jump measurement case. So I have explained TUR for continuous measurement, and in previous QTUR, I assumed that the system is in a steady state. So how about other kind of observable other than continuous measurement? And how about the system out of steady state? So in continuous measurement, we can divide the whole system into principal system and environment. And we obtain the jump record by measuring environment. So this scenario can be generalized to this very simple model. So we have system whose initial state is psi, and environment whose initial state is 0. And S and E interact via unitary operator U, and we measure environment after the interaction. So this is nothing but a general CPTP. So this is a CPTP, and because this G is an Hermitian operator, we can eigendecompose, and Gm is eigenvalue, its phi m is eigenvector. Then the whole state, including both S and E, time evolution of whole state can be given by this one, and by introducing operator given by this one, this is a cross operator, then this whole state after the interaction can be represented by this this expression. So this is a cross operator. So if we trace out the whole state, then of course we recover a conventional cross representation. Then I'm going to obtain the TUR for this general system. Suppose the environment basis given by this one, and suppose that this eigenvalue satisfy this condition. So G0 equals 0 condition. So this condition is not strict because this condition corresponds to defining the standard point. Because if we do not have this condition, average of observable can be arbitrarily large while keeping the variance constant. So any Hermitian operator can be satisfy this condition by shifting eigenvalue. So this is an example of shifting the eigenvalue. Then it is possible to derive TUR for CPTP. So this is a representation of TUR. So here, this part is variance, and this is mean, and Xi is represented by this representation. So here, V0 is a cross operator corresponding to the zeroth eigenvector. And this Xi is similar to the dynamical activity in classical system, because suppose we this eigenvector psi 0 is the same as the environment, then this V0 corresponds to 0 U0, which means that this cross operator V0 is a cross operator when the environment is not changed. So inverse of V0 corresponds to the larger activity in the CPTP. So this representation is the analog of the dynamic activity. And this relation holds for any CPTP as long as this part is positive definite. Because we have to calculate the inverse, of course this part should be positive definite. And any observable G applied to environment as long as this condition is met. And as I said, this condition can be satisfied by shifting eigenvalue and any initial density operator rho in S. And this is for example, because of course a continuous measurement can be represented by CPTP. Let us consider continuous measurement case. So V0 can be computed like this one, and observable is when we consider the counting observable. Counting observable naturally satisfies this condition. Therefore, CPTP TUR becomes this representation. And this relation holds for any thin blood dynamics and any initial density operator. And when the HT and L, T is time dependent, then we have to place time ordering operator here and here. Because basically the same expression holds for time-driven case. So derivation of this CPTP TR is similar to the previous TR. So we use quantum Cramér-Rao inequality. But as I said, it is difficult to calculate quantum Fisher information. But this paper obtains upper bound on the quantum Fisher information for open quantum dynamics, CPTP. And they found that this relation holds. Here, H1 is represented this one, and H2 is given by this one. Here, VM is cross operator. So there's simple expression. Then, similar to the previous case, we consider parameterization of VM like this one. But because the cross operator have to satisfy the completeness relationship, this relationship should be satisfied. So we cannot parameterize like this for all VM. So this is emphasized because from 1 to m is parameterized like this, and V0 should satisfy is determined so that this complete relationship is satisfied. And V0 can be represented by this expression, and substitute this expression into this upper bound, then we can obtain CPTP TR, this one. And this derivation assumes initially pure state, but it can be generalized to initially mixed state through the purification. So this is the final result. And next, I would like to show the connection between quantum speed limit and TR. So quantum speed limit is about trade-off relation between speed of time evolution and cost in quantum dynamics. And for a simple case, we have some closed quantum dynamics, and let tau be a time required to satisfy this orthogonal condition. Then QSL states that the tau should be larger than this quantity. And this bound is Mandelstam time bound, MT bound for short. Then let me unify QSL and TR. So QSLs have been derived for several dynamics, closed quantum systems, open quantum systems, and classical stochastic processes for recently. While QSLs focuses on the transformation of S, the quantum TR is concerned with the evolution of E. So as I explained in the previous slide, TR, I have derived TR for CPTP, and I focus on the operator in the environment. On the other hand, for the case of QSL, we are interested in the time evolution of S. So QSL and TUR bound the evolution of the complementary states by thermodynamic quantities. So in order to unify these two QSL and QSL and TUR, let me use time evolution of CMPS state. So we have this kind of, suppose we have this classical stochastic process, and there is a jump at S1, S2, S3, and S4. And as I said, this kind of Markov processes can be encoded to CMPS state. And this jump state is represented by an operator which creates particle in the field. So this jump information can be represented by this plate. So now we are interested in the time evolution of this GMPS state itself. So this direction is time evolution of original Markov process. On the other hand, this horizontal direction is a time evolution of GMPS state. So we are now considering one-dimensional higher space. So that's why I write bulk and boundary spaces. So this is some example of bulk boundary correspondence. So we are going to consider this a time evolution of this GMPS state. But we can see that the size of this GMPS state are different for different time. So we see that for earlier times, this plate is shorter, and at this time, the plate is longer. Because when we apply the QSL, we have to compare state at different times. But because the dimensionality at this time are different, we cannot compare this GMPS state with this GMP state. So we have to scale this GMPS state. So if we scale the GMPS state, we have this dilute GMPS state. So in terms of the number of jump, this plate and this plate have the same information, just slower dynamics. So recall that GMPS is represented by this equation. Here, UT is an operator which records the jump events in this vacuum state. And by the scaling, I explained in the previous slide, we have this kind of modified unitary operator. So difference between this original GMPS operator and this scale operator is that the integration range are different. For the original case, the integration range starts from 0 and end at t. So, but for the case of this scale operator, we have the integration from 0 to tau. And this integration does not depend on this t. So this unitary operator is a scale version of unitary operator. Because by using this representation, we see that the time evolution of GMPS state becomes conventional quantum mechanics. So, in principle, any relations which hold for quantum mechanics should hold for the time evolution of GMPS state. So this is the main idea of this work. And so we can consider, for instance, QSL or Heisenberg uncertainty relationship for this time evolution of this GMPS state. So let us start with speed limit, applying this QSL to time evolution of GMPS. So first, I'd like to review basics of speed limit. So speed limit is all about triangle equality. So suppose we have state S. So state S may be a density operator or pure state for quantum case, and for the case of classical stochastic process, S corresponds to the probability distribution or probability density function. And we can define the distance between state. And let S0 be initial state, and S tau be the final state. And we can define intermediate state SD. And if we define distance, then this triangle inequality holds, because distance measure should satisfy this kind of triangle equality. And by applying this triangle equality many times, we have this representation. So here NL is supposed to have infinitely large value. Then this triangle equality can be represented by this figure. Here, this is a straight line, so this is the shortest distance between initial state and final state, which corresponds to the left-hand side. And right-hand side is distance along this time evolution of S. So by using this simple triangle inequality, basically most of speed limit can be obtained. Of course, there are some exceptions, but most of speed limit can be derived by this simple equation. For instance, when we employ, suppose we are considering quantum dynamics, and if we use bridge distance, then this relationship reduces to geometric QSL. And for the case of classical system, when we employ the total variation distance and probability distribution for S cell, this reduces to found in this one. And if we use Utter's distance, then found by this one. And when you consider the Wasserstein distance, which is recently actively studied in stochastic thermodynamics, then this relationship directly yields Wasserstein distance for entropy production. Let us consider bridge distance, for instance. So we have pure state. Then bridge distance can be represented by this expression. Here, FID is a fidelity, quantum fidelity, so overlap. For the case of pure state, it's an overlap. And we can compute the infinitesimal distance between psi t and psi t plus dt. And it is known that this part becomes quantum Fisher information, which is also known as Fubini study matrix. Then substitute this expression into this triangle inequality. Then this very well-known geometric QSL can obtain. And by using this geometric QSL, it is possible to derive empty bound. For instance, for closed quantum dynamics, then this quantum Fisher information becomes a standard deviation of Hamiltonian, and this part becomes pi over t, I think. So let me use this geometric QSL for the time evolution of Shin MPS state. So as I explained in my previous slide, we are considering the scale CMPS and consider the time evolution in this direction. So as I said, this direction is a time for original Markov process. And key inequality is monotonicity. So this distance, bridge distance, satisfies monotonicity. Here, E is CPTP. So basically, this inequality shows that if we use partial information of state, then the distance should be smaller than the original distance. And considering only system or environment responds to applying trace operation. So this is CPTP. So of course, this operation should satisfy this monotonicity relationship. So first, derive QSL from time evolution of CMPS. So we have this CMPS state. And when we substitute CMPS state to the geometric QSL, we find this representation holds. And because in QSL, we are only interested in the time evolution of system state. So we are only interested in this part. So this is a whole CMPS state, including both system state information and field which records jump records. Because considering only system corresponds to CPTP, the monotonicity inequality holds. So this inequality directly yields this type of speed limit, which is a particular case of the QSL derived in this paper. So next, derive TUR from the time evolution of CMPS. So we have this geometric QSL, and now we are interested in the field state. So this is essentially the same, but some difference. There is some difference because it is almost impossible to obtain field state. So this is geometric QSL for the CMPS state, and there is a hierarchy regarding the amount of information. So original CMPS state has both system state and environment state, which includes a recourse of jump event. And if we are interested in field state only, of course the information is less than original CMPS state because the system information is discarded. But it is in principle impossible to obtain field state. So but we can obtain some observable probability distribution. But of course, observable probability distribution has less information than field state. In this case, field observable corresponds to counting observable, which counts the number of jump events. But this quantity can be computed, can be obtained, but still it is difficult. So we may replace this information with mean and variance of field observable. So in this case, this corresponds to the mean and variance of counting observable. So by using monotonicity, this part should be lower bounded by term, including the counting observable mean and variance. So this is the essence of the derivation. So I'll skip the details, but use some inequality. So by using the monotonicity relationship, we arrive at this TUR-like inequality. So left column corresponds to classical case, and right column corresponds to quantum case. And the top inequality is derived from applying the monotonicity inequality. And these lower inequalities can be derived from the top inequality. For instance, this part, this well-known TUR, bounded from below by dynamic activity, originally derived by this paper. And this holds for steady state case. And this bound is obtained by this paper, and this TUR holds for non-steady state case, but the left-hand side is not scaled variance. This part is not average. So this quantity is very difficult to observe with experiment. And this inequality is obtained by this one, and this holds for non-steady state case. But we see that left-hand side can be represented by a scaled variance. This part, this double square bracket denotes standard deviation. And right-hand side is exactly the same as the left-hand side, except that this A term is replaced by B. So B is a quantum dynamical activity, and A is classical dynamical activities. So these relationships have been derived for the first time in this paper. So this is a whole picture. So we have some original GQSL, geometric QSL for CMPS state. If we are interested in the system, then we have speed limit, and if we are interested in the field, then many TURs derived. And left column is a classical case, and right column is a quantum case. And because I mentioned that when we consider the time evolution of CMPS, it is nothing but conventional quantum mechanics. So in principle, any relationship which holds in quantum mechanics can be applied to the time evolution of CMPS states. So how about Heisenberg uncertainty relationship? which this is Heisenberg uncertainty relation generalized by Robertson. And here is this is a standard deviation. This is a commutation, and of course we consider specific position and moment, and we recover well-known uncertainty relationship. So let us consider this Heisenberg uncertainty relationship in the time evolution of CMPS. So we are considering this uncertainty relation in the bulk space. So recall that scale unitary for the CMPS is given by this one, and we can obtain a Hamiltonian corresponding to this unitary by this simple calculation. And with this, this U can be represented by this matrix exponential. And let she be a counting observable, which counts the number of jump events. Then let us define its Heisenberg picture version of the operator. Then the Heisenberg uncertainty relation provides quantum TR. So this is a Heisenberg uncertainty relationship where x and y, operator x and y is replaced by k. K is a Hamiltonian of which induce the time evolution of the CMPS, and CT is counting observable. Then calculating this quantity, we have this type of quantum TR. So far I'm interested in the counting observable, but how about another kind of observable for the field? Of course it can be used. Suppose we are interested in the correlation. So this is a classical stochastic process having three states. And let us define scoring function which returns some real value for each state. So suppose if we have three states, for instance, then the scoring function would be -1, 0, and +1. Then we can compute the correlation. Then if we consider correlation observable and applying this correlation, then the bound for the correlation can be obtained. So this is a bound for the correlation. So C is a correlation defined by this one. And again, this is a classical case. So this A is a dynamical activity, and S max is a maximum absolute value of the correlation, scoring function. So this is dynamic activity. So faster change in the correlation requires larger dynamic activity. And I won't explain the details about the result obtained from this inequality, but because through the linear response theory, this correlation bound can be related to the bound for the perturbation. So this is my conclusion. So my today's talk is about a relation between quantum TUR and quantum speed limit and quantum estimation and Heisenberg uncertainty relationship. And here, my today's talk is about the relation indicated by this red line. So this is today's talk. So thank you for listening to my talk.
Questions? Can you walk to the
So regarding the CMPS state, if I understood correctly, the particles created in that quantum field correspond somehow to jumps in your system. So I was wondering, how is somehow this unitary picture compatible with, say, irreversible evolution of an open quantum system where you say have certain stochastic jumps that only happen in one direction, whereas the unitary evolution of the CMPS state would somehow always have this L-jump operator tensor, the field operator, but also the Hermitian conjugates, also the reverse process is somehow possible. Can you solve this or explain why it still works?
So basically, as you mentioned, so this jump information is recorded in the quantum field. But if we only focus on the main system or the quantum field, the dynamics is described not by the unitary operation. But if we are interested in the whole space, then the dynamics can be described unitarily. So, of course, for instance, any irreversible process can be described by unitary if we enlarge the space by purification, for instance. But if we are only focusing on the part of the dynamics, then the time evolution is not unitary. So can I answering? I answering your question?
I think, yeah, but I'll probably ask more in the break without taking time from the other.
Thank you for the question.
Yeah, thanks for the talk.
Thanks for the talk and the amazing results. I have a couple of questions. I mean, maybe I can ask about this, just because this kind of came to my mind. So, following on from what Florian was asking, I mean, if the particles here are jumps, right? If I now think about moving forward in time t, I mean, is that red particle there that is pointed at with the particles in figure B, right? I mean, are the particles on the left side going to change, or is it just? I mean, essentially, the jump record is going to kind of increase in time, right? Because more jumps will happen. But the jumps that have already happened, I mean, they're fixed, right? They just happened, right? So, I mean, when I think about the dynamics moving along the t direction, is it simply that essentially the space is expanding and more stuff is happening coming out of the picture, or is there really kind of dynamics where that red thing that has a particles arrow pointing at it is actually going to be moving around? Does it make sense what I'm asking? I mean, I'm just, if those are jumps, then surely isn't the past essentially fixed? So there's essentially there's only dynamics at the far edge, right? Or am I misunderstanding?
So your question about is that so what happens after this place?
Well, if I think about like normal dynamics in some kind of space evolving in time, and I think about how particles would normally behave. If I have a particle here at time, t equals 0, then at some later time, this particle's position could have changed to be somewhere else.
Yes.
But here, that doesn't seem to be the case, right? If the particle is a jump that occurred at 1 second, that same jump has always, as I continue forward in time, there's always that jump at 1 second, right?
Yes.
So that particle never moves, right? It's just fixed where it is. It's simply that I'm adding more particles as I go along. Is that the right picture I should have of this?
Okay, so this is not the exact picture of CMPS, because in this case, some realization of particle creation is represented. But for the case of CMPS, all possible information is recorded. So for instance, this is only a case of this jump, this trajectory, but the CMPS can include all possible jump events. So this is only used for explaining the concept of CMPS. So in principle, CMPS takes all information. So CMPS cannot be described by this place. So I think your question is that this part, this is a jump corresponding to some time, but this part jump does not actually include in actual CMPS state.
Yeah, no, I understand. So you have to sum over all of the possible trajectories, and that gives you the CMPS.
Yes.
Right, okay, that makes sense. I do have another question, but I don't want to stop anybody else.
Does anyone else have a question? Maybe Magdalena first.
I have a quick one that I can let you take the mic again. Yeah, just to clarify, when you were explaining the derivation of the thermodynamic uncertainty relations from the Heisenberg, is it correct that you use the Schrödinger-Roberts form, so the more stringent one?
No, this is I just use this Robertson version.
Yeah, that's right. So I wonder if you use the Heisenberg, does it change a lot? I mean, are there any alternative, weaker but still uncertainty relations one would derive?
Yes, it is possible to apply this different kind of uncertainty relation to this kind of fusion of CMPS state. But when we derive some inequalities, basically we can obtain infinitely many inequalities. But the important point of the thermodynamic bound is that the bound should be physically interpretable. And if we use different kind, for instance, I tried other kind of uncertainty relationship, then we obtain some extra term, but which cannot be physically interpreted. Okay.
So I think we have time for one more question. Yeah, please.
Yeah, hi. So usually when you have these Fisher informations for these CMPSs, it's a quantum Fisher information, and so it involves, in principle, a maximization over all POVMs of this larger space that also involves the environment, right? And that therefore includes possibility of having non-local measurements where you measure, your MPS, your environment. You would be measuring different positions or different times. Is there any notion that you can make a stricter bound using some kind of maximization over local measurements in your CMPS?
Yes, I think it's a very important question. And so currently my answer is, because I think that your question is that there is a possibility to obtain more stricter bound by using different kind of local measurement. So I think it should be possible to obtain such measurement, but satisfying for the case of classical primary round equality condition can be easily satisfied because it's essentially that Cauchy-Schwarz equality. Because for the case of quantum primary round equality condition is not easy to obtain. So at this moment, I don't have succeeded to obtain optimal measurement which saturates this kind of bound.
I guess we can thank